postdoc in the Julia lab here at MIT. And I work on this package called Conductor.jl, which is for neurophysiological modeling of neurons and networks of neurons, in this case, biological neurons. Just start off with some motivation. Why would I make a package like this? As a neuroscientist, I would like to derive insight about biophysical dynamics that underlie neurobiological phenomena that we can observe in a laboratory setting. And I'd like to learn these dynamics from experimental data. And these days, most mechanistic Got it? Okay. Most mechanistic neurophysiological models are defined implicitly through monolithic simulator engines. And these engines, they're pretty good at doing forward simulation. They've been developed for decades. They've had countless hours, engineering hours, and domain expertise poured into them. But where they don't do so well is data assimilation tasks. And that's simply because you cannot readily differentiate through code generated by simulator engines, nor can you really exploit the structure of the latent space of your model if you're trying to do something like Bayesian inference. And so as a result, the prevailing approaches to optimization and inference with these types of models have been constrained to black box approaches. So if you're talking about optimization, that means you're using heuristic approaches like evolutionary algorithms, and then likelihood-free inference approaches. And that's really kind of a shame because this is a really hard inverse problem to solve. And so in order to take advantage of the latest advances in optimization and inference, I'd much rather prefer to do this in a programming language with pervasive automatic differentiability, with state-of-the-art differential equation solvers over which we can do sensitivity analysis, and composability such that if we wanted to, we could embed our models into, say, a probabilistic programming language. So the value offer of Conductor is quite simple, and that's that it's an abstraction layer that sits on top of Modeling Toolkit and attempts to ease the process of taking familiar representations of neuroscience models and getting them into a format that's compatible with Modeling Toolkit. And that's so that we can get a symbolic intermediate representation that we can run analyses over, that of course we can structurally simplify, and then ultimately lower into native Julia code that is performant and that might be otherwise difficult, tedious, and error-prone to write down by hand. And critically, we want whatever code we generate to be immediately usable by the downstream tools that we're targeting, aka differential equations. So as I said, Conductor is an abstraction layer, and it defines its own sets of systems and types that sit on top of Modeling Toolkit. And really, these are just extensions of the system types that you're used to seeing if you've ever used Modeling Toolkit before. And there's two reasons for doing this. One is because it gives us some extra metadata that we can use to do better consistency checks and also semi-automate some of the bookkeeping work that's involved in building up these kinds of models. So for instance, Conductor defines physical primitives, and primitives are just an extension. They're just symbolic variables, but they have extra metadata embedded into them so that we could tell things like if we have a current, we can tell what kind of ion type that current pertains to, so without having to rely on naming conventions. And the second reason for doing this is quite similar to what Catalyst.jl does, and that's that when you have a representation of different systems, that mono representation can often be lowered into multiple different types of systems at the level of modeling toolkit. So if you're talking about a conductance system for a membrane ionic current, that could be represented as a deterministic process, so you would lower to an ODE system. Perhaps you want to account for noise in your channel, and so you do an SDE system, or you want to go to a full-blown simulation of a Markov process and lower it to something like a jump system. And similarly, Conductor has compartments, which are just an abstraction for a generic abstraction for neurons. A compartment can be a point process. It can be something with geometry that is ascribed to it. It could be an assemblage of multiple compartments. And so you could have that expressed as either an ODE system, an SDE system, or if you want to get into detailed morphology, you can describe it as a PDE system as well. And as I said, these just lower down into the regular systems that you're used to from modeling toolkit. So what does this look like in practice? Well, here's some example code of where you would build up just your standard Hodgkin-Huxley neuron with some stimulation. We would start out by defining our first primitive, which is just a membrane potential. That's a symbolic variable that you can use to write equations. And here I'm just defining the kinetics of gating particles in the Hodgkin-Huxley paradigm, where you have your forward and reverse rates for the activation kinetics of this channel. And that can be repeated and combined, and so then you can have build ion channel systems where you dictate, okay, this is the type of ion current flowing through it, these are the kinetics, this is the maximum conductance. We can collect these things together, create more primitives for the equilibrium potentials and the types of ions that they pertain to. To give our model simulation some activity, we can define a stimulus, in this case a pulse train that has a square wave pulse of a certain amplitude and a certain duration in the middle of our simulation. And then we can apply one last final annotation, and that's to say, hey, all these systems that we're giving to you, they should be treated as a Hodgkin-Huxley system. So that means the equation below, we should know to sum these currents, that each of the currents should have a paired equilibrium potential with it. And so, like I said, these are extra consistency checks that we can do to make sure that your system makes sense physically. And so there you go. You can just run that into a simulation or into a differential equation solver like you would normally, because as I said, the output of the simulation function here is just an ODE problem. So what does that look like? Well, as I said, an excitable membrane that you've stimulated in the center, but we can go on to do more complex things. So we can create more exotic patterns by adding in more currents. Here's the membrane potential in the somatic compartment of a neuron where I've stimulated a separate dendritic compartment. We can build these up into networks of interacting neurons. And as I look at this slide, I can see that I have an unhealthy obsession with bursting neurons. But you get the picture, right? So that's all well and great. Can we start now? So we've kind of like reached parity in terms of, okay, I can forward simulate. Can I start to do some of these things that I was talking about that would help with solving inverse problems? And this is a very simple toy example. But here I'm just taking a model, I'm randomly initializing it and saying, hey, can I, based upon just the observable voltage potential in my target data, can I find the parameter values that would recapitulate this data? And it works pretty well. So in the future, where am I going with this? I'd like to have more detailed morphology. So right now you have the possibility of describing multiple compartment neurons, but I'd like to be able to lower those to PDEs, also with importing morphological data from sets like the Allen Brain Institute. As I said, lowering to different types of systems. The default right now is ordinary differential equations. to incorporate local learning rules if you wanted to do something like STGB, because if you want to adjust parameters, right now it's just through backprop. And the big thing that's coming up is I have just started a collaboration with the ProbComp group at MIT. And so I'd like to make a very tight integration with Jen so that we can do things like Bayesian model selection and more advanced inference methods like sequential Monte Carlo, particle filtering, things like that. And so I just finished with a thanks to the Julia Lab, Alan and Chris for supporting me while I climb up this mountain. And in particular, some key contributors that helped in the very early stages of building up what eventually became Conductor. So Drava, who was formerly a postdoc in the Tim O'Leary lab, and Srinivas and Alec, who were formerly in Eve Martyr's lab. So that's what I got.
Thanks a lot, Wiktor. Are there any questions from the audience? Yes, sure, yeah.
Hi, thank you very much. So in more complex Hodgkin-Huxley-like models, we have it in cardiac, I'm sure in neuroscience you have it. Many times we have these if-else rules.
Yep.
And that's the problem with gradient and inverse problems. How do you try to answer those kind of problems?
So it's situation dependent. One of the main reasons that I wanted to get things into a symbolic format is because then you can start searching through and looking for potentially non-differentiable operations and replacing them with smoothed approximations. Or you can leave in the original one and write a chain rule so you can get a surrogate gradient for whatever you're working with. In some other cases, you might have to do something that's a little bit more complex. A great example is discrete probability. So when you're modeling synaptic release, that's a good one where you might have a probability of release instead of having a continuous process. And so for that, we're exploring solutions. There's stochastic AD that the Julia Lab has developed, but there's also ADEV, which is a similar effort by the ProbComp group here at MIT.
So, but do you approximate a Heaviside function with a sigmoid function?
You could. That is one way that people do it. That's certainly one way people have approached it. In fact, in this toy example, there's a min function that I had to put a smooth approximation in there to get that to work, because there was a minimum set on, I think, calcium concentration. But it's something that you can go do because everything your modeling toolkit models are expressed in Symbolic. Symbolic has substitute rules, so it's quite possible, and that's actually one of the things that I'd very much like to get to is to kind of suggest to the user if they aren't aware, right? To say, hey, we've gone through and looked up common operations that would introduce a discontinuity here. You might want to make these substitutions. We could do some of that